Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Today, inshallah, is the last lecture of the last session, session 14, which is about regression. Inshallah, today we'll talk about residuals of regression. Last lecture, we talked about errors in estimation in general, and we defined the error in estimation as the difference between the actual value or the observed value and the estimated value. And we mentioned that some errors are of course positive and some are negative based on the estimation that we do. And to measure the size of the errors, we defined the root mean square error. The root mean square error is computed as follows. We compute the errors for all possible values of the response variable, the y variable. We square them, and then we take the mean of all of these squared errors, and then we take the square root of that mean. And that's what we call root mean square error. And of course, as the error is very small, that means that the estimation that we did is very good. If the error is very high, of course, the estimation is bad. Now, we define residuals as the error in the regression estimation. So residuals are errors, but this word is usually used in regression. And one residual is corresponding to one point x and y. So for a given observed value of y, if we do an estimation for it and we compute the error between the estimated value and the observed value, this is what we call residual. So the residual is the difference between the observed value of y and the regression estimation of y. And that's exactly how we defined error in the previous slide, but this is special for the regression. So when it is regression, we call it residual, which is again the observed y minus the height of the regression line at x, which is the estimated value of y, which is also the vertical distance between the point and the best line, which is the regression line. Okay, so that's what we saw last time as the red vertical lines. Let's see a demo on that. We will define a function, fitted values. This function will take the table and the two columns as usual and return an array of all the estimated values for the x values. So it will compute the slope and the intercept, of course, using the functions that we defined earlier in the session, and eventually returns the array of the estimated values. We also define the residuals function, which will get the fitted values using this function and then compute the residuals, which are the difference between the observed values and the predicted values. Now let's use that for the Galton dataset, which, as you remember, has the relationship between the mid-parent heights and the children heights. So this is the dataset that we used so many times before. And we will add to this dataset or this table two columns, one with the fitted values and one with the residuals. So here is the new table. And then let's compute the correlation between the mid-parent height and the child height. We will see that the correlation is 0.32, which is positive correlation, but that's not too strong. Then we will define a function called plot residuals. We will have here two plots. So we will create a table in which we will have the fitted values and the residuals. Then we will draw the scatter plot of x against two variables, y and the fitted values. And also we will have a new scatter plot, which is the residual against the x values. Now let's draw these two plots for the heights dataset. So the first one is the usual one. We see the original dataset, original scatter plot, along with the regression line, which are the fitted values. We will also have another plot here, which is what we call the residual plot. So the residual plot is the scatter plot of the residual values against the x values. So what we see in this plot is the errors. So for the values, for each value here in the original scatter plot, we will compute the residual for it, and then we will plot it here. So when we see that for the heights dataset, we'll see that the residuals or the errors are almost symmetric across the horizontal line. So usually when we look at the residual plot, we will have the horizontal line here as a reference. Why is that? Because the horizontal line means that we have zero error, which means that this is the line that is referring to the regression line. So any point on that line means that this point is on the regression line. Any point that is deviated from the horizontal line means that the error is positive or negative, which means that the predicted value is not exactly the observed value. So when we look at this residual plot specifically, we'll see that the residuals are symmetric above and below the horizontal line, which means that the linear regression for this case is a reasonable choice. Okay, whenever we see in the residual plot that the residuals are distributed symmetrically above and below the horizontal line, that means that the linear regression is good for this relationship. So is that the case with every data set? We will see. So let's get back to the slides. We will continue with another demo, which is called dugongs. So dugongs are types of marine animals in which we can estimate the age of them given their length. So let's see a demo on this data set, and we will have to get, and then we will draw a conclusion. The dugongs data set has two columns, the length and the age. Now let's plot the scatter plot of this data set. So we'll see that there is, of course, a positive correlation here. There is a positive correlation between the length of the animal and the age of that animal. So let's compute the correlation. We'll see that the correlation is 0.83, which means that there is a strong correlation, which means that there is a strong linear association or linear relationship. Now let's plot the residuals. Let's see the original scatter plot with the predicted values and also the residual plot. If you look at the original scatter plot, you will see that the estimated values are well representing the data set, except in this part maybe, and also in this part. Now let's look at the residual plot. Looking at the residual plot here will show that there is a big difference between this and the previous one that we saw earlier for the heights dataset. Here you will see that it is almost symmetric, as we said, across the horizontal line. Here this is not the case. We'll see that it is positive, the residuals are positive here, then they started to be negative here, then they started to be positive again. So that's kind of a pattern in the residual plot. And whenever you have a pattern in the residual plot, that means that linear regression might not be a good choice, and there might be some non-linearity in the association or in the relationship between the predictor variable and the response variable. That was not again the case here. There was no pattern at all here, so that means that linear regression is good. Although the correlation over here was not that strong like the animal data set, but still the relationship was linear. Here, although the correlation is really high, which means that there is a linear relationship, but it seems like from the residual plot, it seems like the nonlinear relationships are even better. So whenever we see a pattern in the residual plot, that means that the linear regression is not the best choice. Let's do that also on another dataset, or a third dataset, which is called US women. In this dataset, we have two columns. We have the height of women and the average weight of them. So let's draw the scatter plot here. You will see here that it is very linear, or at least it looks very linear. Let's compute the correlation. The correlation here is 0.995, which means that there is very strong positive correlation between the average weight of women and their height in the US. Let's plot the residuals. Let's have these two plots, the plot of the original scatter plot, okay, which looks kind of nicely fitting the original observed values. Now let's look at the residual plot. And this is a big surprise here. So the residual plot is exhibiting here a very clear pattern. So with positive values getting decreased, then negative values increasing, then negative values decreasing, then positive values increasing. So that is clearly a pattern. That is clearly not symmetric across the horizontal line. So that means that the linear regression is not the best fit here. And actually, if you looked at the original scatter plot, you will see that there are some positive residuals, here negative, here positive again, and so on. So it seems that maybe a nonlinear regression will be a better fit here. So although the correlation is very, very high, actually is very close to 1.995, but the linear regression here is not the best choice. So the residual plot helps us finding whether the linear regression is a good choice for the relationship that we are studying or not. Looking at the residual plot is like a zoom into the errors of the linear regression, and that shows us whether linear regression is really good or bad for this relationship. Now let's see another dataset, which is the dataset that we used last time, the demographics dataset. In this dataset, if you remember, we have a row for each district, and for each district we have the income, the percent voting for Clinton, and the percent of the population who went to college. Let's compute the correlation between the median income and the percent voting for Clinton. This is the correlation. It seems like it is very weak correlation. It is positive, but it is very weak. It is 0.18 Let's see how the residual plot will look like. So here is the original. So let's look at this first. So here is the original scatter plot with the fitted line. And of course it is positive, but you see that the points here are not clustered very well across the line. That's why the correlation is not that strong. Now let's look at the residual plot. Remember, the residual is on the x-axis, this is the x variable, or what we call the predictor variable, and on the y-axis is the residuals or the errors. So looking at the residual plot here, do you see any pattern? Of course, there is a pattern. The spread here is much wider than going to the right. So as you go to the right, the spread is getting narrower until we here have a very narrow spread, or at least a much narrower spread than here. So that's a pattern, which means that again the linear regression might not be the best fit, and maybe there is a nonlinear relationship between the median income and the percentage voting for Clinton. Now looking at the residual plot and checking whether it has a pattern or not to decide whether linear regression is a good fit or not is called regression diagnostics, or actually regression visual diagnostics. And the word diagnosis, of course, means that we want to find out if there is a problem or not. So what we saw in the previous demo is what we call visual diagnostics. And for visual diagnostics of regression, we use what we call the residual plot. So the residual plot is a scatter diagram of residuals. It is used to check whether linear regression is appropriate, is reasonable, is a good choice or not. It should look like an unassociated blob for linear relation. So if there is really a linear relation, then we should see that the scatter plot has no pattern at all. Then the residuals are completely uncorrelated with the predictor variable or the x variable. If there is nonlinear relation, then we will see patterns in the residual plot. So what we need to do when we look at the residual plot is to look for curves, trends, changes in spreading, outliers, or any other pattern. If we see something like that, that means that linear regression is not the best choice. Now let's talk about numerical properties of residuals. And we will start by a question. What is the average of the residuals? So if we are predicting the values of y given x using linear regression, what will be the average of the errors or the average of the residuals? A related question is, Will our answer be different in the case of nonlinear pattern than the case of linear pattern or not? Let's see by a demo. So let's try to answer this question by looking at different data sets. So let's compute the average of the residuals of the heights data set. So we get 0. The average of the residuals of the dugong data set, 0. How about demographics? 0. Okay. So it is a fact that the average of the residuals are always 0. So when we have linear regression and we compute the residuals and we compute the average of those residuals, as we said, some of them will be positive, some of them will be negative, they will cancel out, and the sum of the residuals will be 0, and thus the average will be 0. Now, how about the correlation between the residuals and the predicted values? It is also 0. So the correlation between the residuals and the predicted variable is 0, and it is always the case. With any linear regression, the correlation between the residuals and the value, the x variable or the predictor variable, is always 0. So let's get back to the slides and summarize what we got so far. So the average of residuals is always 0, no matter what the scatter looks like. Just as the average of the deviations from the mean is always 0. Remember, we saw this previously when we talked about standard deviation. If we take the average of a list of values and then we compute the difference between the values and the average and we sum them, we get also 0. And that's no matter what the data looks like. When we defined correlation, we said that the correlation coefficient measures how clustered the points are about a straight line. So if we plot the regression line and we found that the observed values are clustered very well about the regression line, that means that the correlation is high. If they are not very well clustered, or if they are scattered across the line, then the correlation is small. Now let's quantify this statement through a demo. So we will get back to the heights data set and we'll compute the correlation between the mid-parent and child. The correlation is 0.32. Now let's compute the standard deviation of the predicted values and the standard deviation of the observed values. If we do that, we'll get these values. If we divide the standard deviation of the predictions by the standard deviation of the observed values, we will get that value. Now look at this value and look at that value, and you will see that they are exactly or almost exactly the same. That means that the correlation coefficient is equal to the ratio between the standard deviation of the predictions and the standard deviation of the observed values. Let's try that on another data set, the animal data set. Let's compute the correlation first, which is 0.83 here. Let's do the same, compute the standard deviation of the predictions and the standard deviation of the observed values, divide them, we will get again the same value. Now let's do it on a third data set, the hybrid data set. If you remember, we used it also earlier in that session. If we compute the correlation between the acceleration and the miles per gallon or the efficiency, we will see that it is negative correlation. It is negative correlation. So let's see if that will also apply, or how this will also apply on the negative correlation cases. Let's compute the standard deviation for the predictions and divide it by the standard deviation of the observed values. We will see that we will have the same exact value here, but it is the absolute value. So generalizing this, the standard deviation of the fitted values or the predicted values divided by the standard deviation of the observed values is the absolute value of the correlation coefficient. Or in other words, the standard deviation of the predicted values is equal to the absolute value of the correlation coefficient multiplied by the standard deviation of the observed values. Now let's interpret this equation. We'll do that by looking at the scatter plot along with the predicted values. So here is again the heights data set. So we have the scatter plot of the mid-parent height and the child height, and these are the predicted values. Now let's look at the standard deviation of the fitted values. So you will see that the fitted values here, or the predicted values here, are in the range from, let's say, 64 to maybe 71. While the observed values have a higher range. So it goes from maybe 56 here to 79 here. So we expect that the standard deviation of the predicted values will be much less than the standard deviation of the observed values, and that's why R here is much less than 1. And the observed values here are not clustered well around the line. That's why the coefficient here is much less than 1. Now imagine that these values, instead of being scattered that way, they are much closer to that line. Okay, so it's like we compressed these values around that line. Now you will see that the standard deviation of the line is very close to the standard deviation of y, or of these values. And this is when the correlation coefficient will be higher. If they are almost fitting, if the values are perfectly fitting the line, that means that the standard deviation of the observed values will be exactly the same like the standard deviation of the predicted values, which means that R will be 1. And that's explained why we interpret the correlation coefficient as how much the observed values are clustered around the regression line. Now let's get back to the slides and summarize the relation that we just mentioned. So the ratio between the standard deviation of the fitted values and the standard deviation of y is the absolute value of the correlation, or in other words, the standard deviation of the predicted values is the absolute value of the correlation coefficient times the standard deviation of the observed values. Now what remains is to look into the standard deviation of the residuals. So we saw that the average of the residuals is always 0. How about the standard deviation of the residuals? So one property of linear regression is that the standard deviation of the residuals is the square root of 1 minus r squared times the standard deviation of the observed values. Let's see if that will be the case for any data set and how we can interpret that relationship. So let's get back to the demo. So this is the summary of what we just mentioned. So as we said, the standard deviation of residuals is equal to the square root of 1 minus r squared times the standard deviation of y. Let's try that on multiple data sets. So the first one is the heights. So we will compute the standard deviation of the residuals, the standard deviation of the response variable, or y variable. We compute the correlation, which is, as we saw, 0.32, and then we compute the square root of 1 minus r squared, which is this part, times the standard deviation of the y, or the response variable, and we will see that we get exactly the same value like the standard deviation of the residuals. Let's try that on another data set, which is the Dugong data set. Here is the standard deviation of the residuals. Here is the standard deviation of the age. Here is the correlation, and here is the square root of 1 minus r squared times the standard deviation of the y values, which is, as you see, exactly the same like the standard deviation of the residuals. Here's the third data set, which is the hybrid data set. So here is the standard deviation of the residuals. Here is the standard deviation of the y variable. Here is the correlation. Notice that the correlation here is negative, and here is the right-hand side of the equation, which is, as you see here, it is exactly the same like the standard deviation of the residuals. So no matter what the shape of the scatter plot, the standard deviation of the residuals is a fraction of the standard deviation of the observed values of y, and the fraction is the square root of 1 minus r squared. Now let's interpret that. If r is 1 or minus 1, which means perfect correlation, whether it's positive or negative, then this fraction will be 1 minus 1, which will be 0, which means that the standard deviation of the residuals will be 0. Now let's think about it. Standard deviation of residuals is 0. Remember that we earlier said that the average of the residuals is 0. So now in this case, when r is 1 or minus 1, the average will be 0 of the residuals, and also the standard deviation of the residuals is 0, which means that all of the residuals are zeros, which means that the errors are zeros, which means that the regression line perfectly fits the observed values. So there is no errors at all, which means that it is perfect matching, and that's why the correlation is 1 or minus 1. Now let's check the case when R is 0 or when R is between 0 or 1. To do that, let's use the heights dataset again, and let's plot the scatter plot and also the average line, which is the line at the average value of all the observed values of y. Now if R is 0, that means that this fraction is 1 minus 0, which is 1, which means that the standard deviation of the residuals will be equal to the standard deviation of y. Now let's think together. R is 0 means that there is no correlation at all, and usually that means that the regression line will be just a horizontal line or flat line going through the average value of the observed values. So imagine that this gold line is just the horizontal line now, and that the values are scattered all over the place. That means that the residuals will be distributed exactly as the values of y. Remember that the value of the residual is the difference between the observed value and the predicted value. If the predicted value is the average, that means that we are subtracting every point from the average, which means that we are computing actually the standard deviation of y. And that's why when R is 0, the standard deviation of the residuals is the standard deviation of y. Now if R is somewhere between 0 and 1, this line will start to be different from the horizontal line, and thus the standard deviation of the residuals will be a bit less than the standard deviation of y. And that's why here the standard deviation will be just a fraction of the standard deviation of y in this case. So when R is 1 or minus 1, the standard deviation of the residuals will be 0. When R is 0, the standard deviation of the residuals will be the standard deviation of y, and that's because the regression line will be just horizontal, and thus the standard deviation of both will be the same. If R is in between, which means that it is not perfect line, and also it's not uncorrelated, that means that that line will have a bit of a slope, and thus the standard deviation of the residuals will be less than the standard deviation of y. What remains is one discussion question that I will leave for you. In this question, we are studying the relationship between the scores of the midterm exam and the scores of the final exam. Let's say that for the midterm exam we have an average of 70 and standard deviation of 10, and for the final we have an average of 60 and standard deviation of 15, and that the correlation coefficient is 0.6. Now fill in the blank. For at least 75% of the students, the regression estimate of the final score based on the midterm score will be correct to within some points. Okay, so we want to compute a value here, which will represent the error of the regression estimates for the relationship between the final and the midterm exam. So actually we are talking about residuals here. Okay, so think about it. Think about why we are talking about 75% of the students here. So that ends this lecture, which is the last lecture of the last session of this data science course. That means that the course is over. I really enjoyed so much teaching this course. I learned a lot from the material that we studied together. I also learned a lot from recording the lectures and making them available online. That was my first ever experience with having a course to be available online. I hope that you learned a lot from that course also. Please let me know if you have any feedback about the material of the course or the way the course was taught or recorded. I hope that you enjoyed it also as much as I enjoyed it. Thank you very much. I hope that we will have another online course together in the near future, inshallah. Assalamu alaikum wa rahmatullahi wa barakatuh.